So here we are, final topic. And this topic is only relevant to two of the problems on homework 11. And there's not a whole lot involved with those problems. So you could be electing not to do homework 11 anyway. So, there's not a whole lot of writing on what happens today. Tonight. Man, it's dark out. But this is a logical continuation of things that I have been covering. So it's nice little fast. Okay. So, spherical harmonics. And for some time, we've been dealing with various aspects of solving some sort of PDE, usually the Laplace equation, in spherical coordinates. And so when we're solving a subset PDE, so Laplace equation, Helmholtz equation, or even Schrodinger's equation, they all have a fairly similar form. You get we break the PDE, whichever one you have, down into ODEs corresponding to the three spherical coordinates, so r, phi, and then theta. And what happens is the ODEs corresponding to phi and theta end up being the same. So, here's what we get. The solutions for the phi variable are these 2 pi periodic functions, complex exponentials, where m has to be an integer. And then for the theta part, so going back to the most recent topics I've been covering, we get the associated genre of functions here with evaluated cosine theta. Now, what we've not seen before, we've not seen these strange scaling factors. The only reason we have these scaling factors is to make these two sets of functions orthonormal. So when we integrate any two functions from these families with different indices, we get the result of 0 if the indices are different, and 1 if the indices are the same. Recall this is a Kronecker delta that's equal to 0 for different indices and 1 for the same indices. So if we take these two functions with these scaling factors and just multiply them, those are our spherical harmonics. That's all I've done here. Okay. And because a spherical harmonic is a product of orthonormal functions, spherical harmonics themselves are also orthonormal with a scalar product that just comes from combining these two. So we're integrating from 0 to 2 pi in phi, and then from 0 to pi in theta with this scaling factor of sine theta. So we have, so really just multiplying these two integrals and we get this orthonormality relation. Now, while the spherical harmonics are functions of these two spherical coordinates, if we want, we can express them in terms of Cartesian coordinates x, y, and z. And the way to do that is, because here we have this complex exponential, so if we express that in terms of a cosine and sine of m phi, that's all I've done here. And then we end up with these expressions for Cartesian coordinates in terms of spherical coordinates. Then we're able to express these spherical harmonics in functions of x, y, and z. I'm not going to go through like the whole process of how one does that. But what I will show you is some examples of the results of doing that. Now, these functions, these spherical harmonics, and expressed in terms of x, y, and z, they must be what's called homogeneous of degree 0. So another way of putting it is if you add up the degrees of x, y, and z, the numerator and denominator, they must be the same. So to show you what I mean by that, here are a few examples of specific spherical harmonics. So, okay. Now the superscript is the integer that goes here in the exponent of a complex exponential. So for instance, here we have a 1, so we have e to the I 1 times 5. And here we have a superscript of 0, so there's no complex exponential at all. Here we have superscript of 2, so we have e to the 2i5. And then the subscript and superscript together indicate which associated Legendre function you're going to have multiplying that complex exponential. Okay. Now, actually, yeah, so I'm going to do an intermediate step on this one. Show you how more of a conversion from spherical to Cartesian. So if I take this complex exponential e to the I5 and replace it with cosine, cosine of 5 plus I sine of 5. Okay. Oh, something went wrong here. Not sure where that 2 in parentheses came from. Well, I need to undo here to see why that happened. Okay, this point everything's fine. But something happened between here and here, but that's everything up. Okay. Let's try this again. So all I'm doing is I just want to replace this complex exponential. Okay, with cosine I sine. Okay, so the mysterious 2 did not come back. That's
it
good.
did, but then you kept typing and it went away.
Oh, interesting. Really?
Yeah.
Oh. And at this point, there's an error, so it's just, I think it just gets confused. But
and then put the 2 there.
okay. All right. Now, so what do we have here? We have sine theta cosine of 5. Now, if I compare that to these formulas, here I have sine theta cosine 5. And if I multiply that by r, I would get x. Now, I don't have an r anywhere in here. So sine theta cosine 5, by looking up here, that would be x over r. So that is how the x over r appears here. And here I have sine theta sine 5. So going back to those same formulas, that would be y over r. And so now keep in mind, r is the square root of x squared plus y squared plus c squared. So the degree of the top is 1, if it's linear x and y. R, we have x equals y squared equals c squared, degree 2, but we're taking the square root of that, so the denominator is also degree 1 in x, y, and z. So this is homogeneous of degree 0. This next one, we have cosine of theta, but without any dependence on phi. So if I go back up here, cosine theta is z over r. And again, so it's homogeneous of degree 0. And a bit more manipulation is required here. So here we have so here we have sine squared theta and then e to the 2i phi. So that's going to be cosine of 2 phi plus I sine 2 phi. But then using trig identities, we can express these in terms of sine theta and cosine and sine theta and arrive at this expression. So we have quadratic above and below, still homogeneous to degree 0. And finally, this one, cosine theta is z over r, and then sine theta e to the I phi is like what we have up here, so that's going to be x plus I y over r. So that's how we convert spherical harmonics to Cartesian coordinates. Any questions at this point? Now, the key use of spherical harmonics is to express solutions of PDEs such as the Laplace equation or Helmholtz or Schrödinger's equation. The idea is you express your solution, your general solution, as a linear combination of spherical harmonics, and the coefficients of the spherical harmonics in your expansion are relatively easy to get because spherical harmonics are chosen to be orthonormal. So whatever is multiplying spherical harmonics is a solution of whatever ODE you have in R that comes from separation variables. So when you have separation variables on Laplace or Helmholtz or Schrödinger, like I said earlier, your theta and phi solutions will be the same regardless of whichever of these PDEs it is, but the solution of the R equation will be different. So this solution of that ROD, this is something we had seen some time ago. So the idea is whatever boundary data you have for Laplace's equation, that is used to determine the coefficients, ALM and BLM, of this R part. I'll show you an example of that in a little bit. Similar for Helmholtz equation, the format of the solution is exactly the same. It's just, again, the solution of the RODE is very different. The solution for the Helmholtz equation is in terms of, instead of powers of R like we have for Laplace, it's these spherical Bessel functions that we had seen some time ago. But certain boundary conditions you might have, like for instance, if you're solving one of these PDEs on either the interior of a domain or the exterior of a domain, that could end up ruling out some of these terms. So it just depends on the domain of the problem and the kind of boundary condition you have. So as for how to get these coefficients, we expanded function of theta and phi in a series of spherical harmonics. So it's called Laplace series. So in general, Laplace series has this form. We have these coefficients that are determined using the fact that the spherical harmonics are orthonormal. So, so coefficients are just the scalar products of each spherical harmonic with a function after you're taking the expansion up. Space in there. This is a convention that's used in a textbook where your integrand is to the right of your elements of length, like your d phi or d theta. So I'm not sure why they write it that way, but for consistency, I went along with it. I would think this. Having to conventions. Also, like a difference between American English and British English. Just different enough to cause confusion. Okay, so really tend to work out these integrals. Keep in mind that spherical harmonic is conjugated, and that matters here because, as we've seen by the definition, the spherical harmonic includes e to the in theta, so in general they are complex. So as an example, we're dealing with a Laplace's equation, and the solution has the form v of r theta phi, and we're solving the PDE on a sphere of radius r naught. The boundary condition is that on the boundary of the sphere, so when r is equal to r naught, your solution must be equal to this function that gives so the Laplace equation is used to solve for electrostatic potential. So the electrostatic potential on the boundary of the sphere is given this function f. Now we're solving for on the interior of the sphere, so you have to make sure that at the center, at r equals 0, the solution is non-singular. So if we look back at the general solution for Laplace's equation, if I substitute r equal to r naught, then this whole series, when r is equal to r naught, must evaluate to f. But if I plug in r equals 0, well, this is going to blow up. So we can't have that. So for this situation, we're going to remove these terms. On the other hand, if we were solving an exterior Dirichlet problem for Laplace's equation, where we're solving for electrostatic potential outside of the sphere, then we would include these terms because we're not going to be evaluating it at r equals 0. And we would remove these terms because we don't want the solution going off to infinity as r goes to infinity. So whichever kind of problem you're trying to solve, interior, exterior, dictates which of these terms you use. On the other hand, suppose you're solving Laplace equation in an annulus, so the region between two spheres of different radii, so they're concentric, then you can include both terms. So that does happen. All the situations I just described actually come up in the introductory PDE class, so Math 417, 517, which several of you have taken and one you will take soon. Yeah, I remember covering that of those situations. Well, that was actually in 2 dimensions. So we weren't dealing with spherical harmonics then. What we had here was a lot simpler. We just dealt straightforward sine and cosine. Okay. But yeah, because in 2 dimensions, you just have polar coordinates. So you have something like this for the r part, and for the theta part, you just have this. So basically, sine anything 2 pi periodic. So sine and cosine would be enough. Okay. So, imposing our boundary condition, we set r equal to r naught in here, but then this must be equal to f. But f itself is going to have this Laplace expansion, where we have these coefficients, CLM, that are defined in terms of these scalar products of spherical harmonics with f. So all we have to do is match these up. Because the spherical harmonics are orthonormal, therefore certainly linearly dependent, it's enough to make sure the coefficients agree. So we just match these up, and that tells us how to get ALM. It's just the coefficients of f Laplace expansion, and you said to divide by r naught to the L to account for where the boundary condition is being enforced. So summarize what's been happening over the course of several classes. You're solving one of these PDEs on a sphere. So you use spherical coordinates. You separate the PDE using separation variables into your ODEs for your three spherical coordinates. For the phi part, that's just the combination of sine and cosines. For two-part periodicity, for the theta part, associated Legendre functions. So those two together make your spherical harmonics. And then whatever kind of solution you get from your ODE for your remaining variable r, you put that in your general solution, and to figure out how to enforce the boundary condition, whatever boundary condition you have, you make use of a Laplace series for your boundary data, and you match that against a series that you get from substituting a boundary condition. And that will give you the coefficients of your solution that you're looking for. So that's the overall process of solving these kind of PDEs on a sphere. And of course, really much of the time was spent talking about the kind of functions that you get as part of your solution and what kind of properties they have. Oh yeah, good times. So I've reached the end. And yeah, originally had plans to also cover a portion of chapter 18. I found myself running out of gas, and I can imagine that you all were too. So as a reminder, with the homework situation, so a way to set up that for every student, lowest 2 homeworks are dropped, so that undergraduates have a grand total of 11 assignments. Graduate students have 12, because the original rule was 1 drop for them, 2 drop for everybody. The campus will do that, so it's 2 drops for everybody. Also, if so, however many assignments you need to turn in, so that would be 9 for undergraduates, 10 for graduates. If you A-step any assignments, -1, and actually if I'm doing it in an average sense. So in other words, if you have so for instance, if you're an undergraduate and you have average of 100 over 8 assignments, yes, yeah, then that will automatically be an A. So that'd be 9 assignments for graduates. So what I can do is I can take a look at where everyone stands in the grade book. So if I conclude based on the currently available data that you're done, And I can let you know that. It's good to let the students know when they can stop doing homework as soon as possible. Okay. Um, so, do we have any homework questions? Okay. Chandler, I saw you unmuted briefly.
I just said no, thank you.
Oh, okay. All right. Michelle, you good? That's okay. Give me one last. Okay. All right. I guess everybody's accounted for then. All right. Let's blow this top 10.